all, I would like to thank the audience for taking the time and the interest with our talk. My name is Sandro. I'm Associate Research Professor at the University of Minho back in Portugal. And today with me I have Sérgio, which is currently doing his PhD under my supervision. And the title for the talk is Rethinking Trust Execution Environments in the Age of Reconfigurable Computing. And without any further delay, I will just ask 5 minutes of your time, because the idea is I will share 5 slides just that work as a kind of preview or trailer for the talk. The idea is to capture your attention and get you to understand the big picture of all of this work. Okay. So, over the last 2 decades, TEs or Trust Execution Environments has been established as the technology to process and protect security-critical applications in a wide spectrum of domains. On one side of the spectrum, we have like the cloud applications and the servers with Intel SGX, and on the other side, we have like mobile and embedded device that use TrustZone. You should be familiar. So probably most of you are not fully aware, but every single day, you, such as billions of people worldwide, rely on TEs based on TrustZone to, for example, process the online bank payments, or even for biometric authentication on your phone, or simply when you are just watching Netflix that leverage some DRM service, you are leveraging Trust Execution Environment. Well, one of the most common TE approach to implement TEs is this virtual secure processor. And the mainstream technology, as I said, is Intel SGX and ARM TrustZone. And despite the difference of both technology in terms of realization at the low level, they typically provide one secure execution environment in your main application process. The problem with these technologies is that, well, they are struggling in their own security problem. You should be probably aware of those hundreds or dozens of papers published either at academic conference or at some industrial. Well, another well-established TE approach rely on dedicated external secure elements that you mount off-chip but still next to your main processor. Some examples are Apple C2 or Google Titan, but the problem is still this off-chip communication fabric is exposed to an attacker, which means it can perform some kind of probing attacks. Well, these are more or less the so. With our work, we try to come out with a new and rethink way of implementing TEs that parts from the observation that nowadays in industry you have these so-called SoC FPGAs, where you don't have only the hard processing systems like dual-core, quad-core ARM processors like Zen7000, but you still have your FPGA technology that typically is embedded in these SoCs for acceleration, flexibility, and all of that purpose. And the idea was basically to leverage this FPGA technology to provide additional security guarantees on a different model of TEs. Well, we call this model TOV, Trust Execution Environments on Demand. We depart from the TrustZone architecture that we'll explain a little bit later in detail. But the idea is to get a bit rid of this virtual secure processor and leverage the FPGA to instantiate soft cores or soft processors that create dedicated enclaves to run fully isolated trusted applications, in the sense that we do not share the same processor, we do not share software infrastructure. And basically we do this on a per application and per demand base, in the sense of the flexibility that the FPGA provides. Okay. At this point, I think you got more or less the idea of our work. We will now dive into the details. I will start with the motivation and goals and threat models. Then Sérgio, which basically was the student doing the heavy lift part of this work, will explain design, implementation, evaluation, and the use case with the Bitcoin wallet. And I will jump back at the end of the presentation, just share some final thoughts. Well, start from the beginning. I will start all of this story with this claim, which is mainstream operating systems cannot be trusted. I have the security experts here in front of me. You probably agree with me, but I will reason a little bit more about this. And by mainstream operating systems, I'm talking about the big monolithic piece of software that typically power our computer, laptops, and mobile devices. I'm talking about Windows, Linux, or Android. And the reason to not trust them, it's all about math and statistics. I mean, this piece of software has millions of lines of code, and the cleanest and best example to explain this sentence is this one. Large is your code base, the more complex it is, probably word about the spaghetti code thing, the more likely you will find bugs, defects, and vulnerabilities on your code. And a very nice exercise that I typically do with my students is the following. Let's imagine, let's take Linux. Let's not imagine because you can do it. Let's take Linux as a target. Let's use one of those softwares that is CLOP. It basically counts the number of software lines of code that you have in Linux. I target just for ARM64 architecture to not include like RISC-V, Intel, and a lot of other architectures. I exclude a bunch of stuff, kind of language that doesn't interest a lot, and we end up with these numbers. And basically you can see like the number of C files, header files, assembly files. The other files are there. I try to exclude that, but I mean, this tool is open source, it's not perfect, but still translates the idea that I want to convey, which is on your right side at the bottom, you see more than 20 million lines of code. And this is basically how big Linux is. Another interesting thing in industry is one metric that we have that is considered the defect rate. Defect ratio. That it stands for the number of bugs expected per 1,000 lines of code. Typically in pre-production systems you have one, the defect ratio is 1, which means where you have 1 bug per 1,000 lines of code. When you ship your product, standard from industry is 0.85. But let's take one very positive defect ratio of 0.1, which means you have 0.1 bugs per 1,000 lines of code, which if you multiply by the 21 million lines of code of Linux, well, there are more than 2,000 disasters waiting to happen. I mean, the relation is not exactly like this, but I think this more or less supports the idea or conveys the idea that I'm trying to explain. This big piece of software cannot be trusted. Well, in this sense, industries start to look in alternative ways to provide like additional security warranties. And NTEs, which started to be introduced a couple of decades ago, in particular with TrustZone in 2004, start to gain traction among the industry. But for those not completely familiar with TEs or trust execution environments, should be asking, what is a TE? Well, I will say that the definition of TE has been evolving over the years, and there are multiple in the literature, but I will pick just the one that is used for one of those organizations working towards the standardization of TEs in mobile device, which is Global Platform. And the Global Platform defines the TE as a secure area of the main processor of a connected device that ensures sensitive data is stored, processed, and protected in an isolated and trusted environment. And more or less, this image, without being pegged to one particular technology, translates that idea. On the left side is your left. On the left side is the normal state, where you run your normal or non-critical applications, and in the main processor you have some sort of hardware technology that you can create a secure state when you process your security-critical applications. Okay. One of the most used technologies to implement TEs is this ARM TrustZone thing. Okay, ARM has introduced TrustZone in 2004, almost 2 decades ago, and the TrustZone is centered around the concept of two protection domains. On one side, you have the secure world that you typically ship a trusted kernel and you put atop different trusted applications. On the left side, you have the normal world where you typically run a rich execution environment in mobile device, Android, for example, and you run atop this rich execution environment the client application that typically requests service from the secure world, from the TAs, and everything is interfaced through a privileged layer of software called secure monitoring. Well, on my research group, we have a strong line of research around TrustZone, and intrigued by the fact that we have been witnessing over the years several vulnerabilities affecting TrustZone. In 2018, we decided to start working towards one paper that was published in 2020 at the SAP Auckland, which is the conference in the academia for system security, where we basically provide a comprehensive picture about the vulnerabilities affecting TrustZone assisted TEs. And for that, we analyze hundreds of CVEs and we reverse engineer the most popular TEs, which was Trustonic, Huawei, OPT, and all of that stuff. And from this study, we grouped the different vulnerabilities in three categories. Ones are the architectural problems or the architectural issues. The other ones are the implementation bugs in the different components on the secure side. And the other ones are the underlooked properties of the art. But a nice and interesting observation coming from this study was that there were a particular architectural flaw that, together with the number of bugs in the implementation of the secure world software, make it practical to basically create privilege escalation attacks on TrustZone. And there was a particular guy whose name may sound familiar among the audience, which is Gal Beniamini, that you could find this guy everything year in Vegas, basically at Black Hat, demonstrating how he found a new way to basically exploit the Qualcomm TE. And more or less the idea is that you run a malware on the unprivileged level on the normal world side, and by basically tracking and exploiting a bug in a TA, you can basically create a privilege escalation attack, and you are able to jump in the trusted kernel. And once you control of the trusted kernel, because of this architectural flaw in terms of the TrustZone architecture, you can access everything. You can access the Android system, you can access other TAs, and you can bring the full system down by basically writing zeros in SKU monitor. And this is quite practical, and there are a couple of CVEs that support all of this. Well, another interesting observation coming out of this study was that micro-architectural side channels attacks on TrustZone are also practical, in the sense that basically you have a shared cache between both worlds, and despite the fact that the rich execution environment cannot directly access the cache lines of the trusted world, it still can compete for those lines, in the sense that it can evict, it can create contention, and at the end of the day, it can create timing difference, which is the most important thing to basically create attacks such as the one as Armageddon disclosed by the people at Grass. And more or less, it's demonstrated that on the microarchitectural side, it's also a problem for this kind of TE. So I just picked two examples. If you go to the paper that we have published, you'll find a lot of different stuff. And the idea is just to explain and provide a bit of context to understand how the TrustZone assisted TEs can be compromised or are flawed. Well, departing from a different perspective, which is this ongoing trend in the silicon industry for these SOC FPGAs, which basically they decide, okay, let's now embed in the same SOC not only the hard processors that you as a programmer typically implement C or C++ programs that translate in assembly. Those assemblies represent opcodes that are compliant with the instruction set architecture. But for different reasons in terms of the trend of specialization, need for performance and flexibility, FPGA, and for those who don't know what is the FPGA technology, is kind of liquid hardware. Liquid hardware in the sense that you don't program at the ISA level, but you have language, HDL language, like VHDL or System Verilog, where you can program, but at the logic level or the flip-flop level. And this, of course, is much better in terms of performance, parallelization, and all of that stuff. And Xilinx created this trend in 2011 with the release of the Zinc 7000. In the meantime, they have released the Zinc UltraScale Plus, and all of this has culminated with the recent acquisition from Xilinx by AMD with a modest and humble amount of $15 billion. And this is basically the trend ongoing in the silicon industry. Well, departing from these problems on TrustZone and this expertise that we gained with that work, coupling together with this trend in industry, in the silicon industry, we hypothesized that if it would be possible to create a model where we leverage the configurable capabilities of these modern SoCs, in particular the FPGA technology, to basically rethink the way we are currently building and implementing TEs. Well, and based on that, we decided to specify the TOD, or Trust Execution on Demand model, that has kind of two rules. First one is, well, when we are kids, we are taught that sharing is caring, but as security experts, we know that sharing is not definitively caring. And this is the first rule. Sharing is not caring for sure, because as we saw, if we share software stacks, if we share hardware structures, at the end of the day, it will be the end game. So the first rule is sharing is not caring. And the second rule is about the principle of least privilege, which basically dictates that each component should be given just the privilege that it needs and assigned with the component that it needs to perform the function and nothing more. Well, and we departed from this TrustZone model with the secure and normal world, and we basically read out of the secure state in the sense that is not shared by the virtual processor, but we leverage the FPGA, is still in the same SoC, but not in the hard processing system, to basically instantiate one enclave that in practice is a kind of soft microprocessor or microcontroller, where we run one and only one trusted application on the top. With this, we basically read out of the trusted kernel, read out of the security monitor in terms of functionalities for this, and at the end of the day, each enclave is given just the specific amount of memory and the right privilege to just access the right components and nothing more. At the end of the day, each TA just access the small tightly coupled memory and a bunch of shared memory to communicate with the other side and nothing more. And each enclave cannot access the other enclaves, neither access the rich operating system. This is compartmentalization at the best. And with that, we define a set of design goals, which stands for provide a dedicated execution environment for each TA, provide the concurrent execution environments, which means multiple, provide physical isolation from the rich execution environment from the other TAs, physical in the sense we are not sharing the same processing system. We are still in the same SoC, but on the FPGA side, which basically gives advantage in terms of not incurring inside channel attacks on the processing system that we have seen that are practical. Reduce the privilege of TAs, because at this point the TA just runs in one specific enclave and just has access to the resource that it needs. Depend on a minimal and decentralized trusted computing base. At the end of the day, for security, trusted computing base is key. And last but not least, to maintain TE software portability, in particular compliance with this global platform standard. I mean, if you develop a model that is too exotic, at the end of the day, no one will use. And our goal was, from the beginning, to be able to run this very same trusted applications that you run, for example, in OpenTE, that is a TE open source based on TrustZone, also in our model. With that, we define our thread model per which TOD should comply with, and we don't trust the rich operating system, of course, it can be compromised. Linux has millions of lines of code. We don't trust in the processing system in the sense that it can issue malicious requests for the FPGA side, it can suffer from microarchitectural side channels. We even don't trust the TAs because we have seen that TAs has bugs at the end of the day, so we don't trust them. We do trust the FPGA bitstream, of course. We do trust the implementation of the soft microprocessors that will power the enclaves, and we do trust that there is a secure boot in place to make sure that the bitstream that is programmed on the FPGA is trusted. We consider out of the scope, I mean, we try we need to minimize a little bit the extent of our problem. We consider out of the scope physical attacks, in particular fault injection. We consider out of the scope side channels on the FPGA. Is something that we are pursuing, but we need to start from something. And we consider out of the scope also denial of service attacks. Well, I pause here for a second. I will let Sérgio continue with design, implementation and evaluation use case, and I will get back at the end.
Thank you, Sandro, and thank you all for coming in. It's a pleasure to be here. It's the first time. Now, going back to the TOD, now that we have design goals and the threat model, how can we design it from that principle? So, but before that, let me just clarify some terms that we are using. This will be basically the same terms that Global Platform uses. We use the term of trusted applications, TAs. That is the application that runs security-sensitive applications, functionalities. Then we have the Trusted Execution Environment OS that only provides the basic OS primitives for scheduling and managing the TAs. Then we have the Client Application, that is the CA, that are just the ordinary applications that whenever they need a security-sensitive functionality to run, asks for it to the TE. And then we have the Rich Execution Environment, that is the mainstream OS that we all know about. So, with no further ado, in our design, we stated that our enclaves are soft-core processors that has an isolated and dedicated on-chip memory, and also the necessary peripherals for their execution. We stated that it is soft-core processors, but we could think about custom accelerator in hardware. But since we are aiming to maintain the portability, and since we have found out from the industry and from the academic that we have a range of soft-core processors available, from the customized to the fully ready to use, and from the low end to the high end ones. So, back into the design, in the software side running on top of that soft-core processor, we have the TA and a little firmware just to provide it the necessary interaction with the hardware. And then we have the TOD agents that provides the management, the upload service, the communication interface between the TAs and the rich execution environment. Then we have the rich execution components, that is the client applications, the rich OS, and a driver to allow the communication. So, how we can convert this design to a real implementation? We choose to demonstrate our design on the Xilinx Superscale Plus. That model has the processing system that has the main cores and the main static hardware, and then we have the programmable logic that is the FPGA, and on the FPGA we instantiate those enclaves as the user wants, and in each enclave we have on the software side we have the TE firmware and the TA, and also the TE internal core API. That is from the global platform specification to provide the minimal interface to the TE components like the secure storage, the shared memory. And then we have the TE communication agent that provides the communication between that enclaves and the rich execution environment. And then we have the TE manager agent that keeps track of what enclaves are available, what TA is running on what enclave, and commands the TE loader whenever he needs to load a new TA to an empty enclave. And on the rich execution environment, we have the TE supplicant, that is a daemon that only provides the necessary information of the location of the TA whenever the TE manager agent needs. So, now let's take a look at our evaluation. We have evaluated our prototype in terms of resource utilization and round trip execution. We choose to develop it on the AVNet Ultra 96 version 2. That is a Zinc Ultrascale Plus. That we choose, obviously, the TOD as the TE, and for the rich execution environment, the Xylem Spatial Element. So, evaluating the resource utilization, we performed 4 case studies at the TOD with 1, 2, 3, and 4 enclaves. Per enclave, we have an ARM Cortex-M1 as soft processor. We have 64 kilobytes of DRAM as the cooled memory. Then we have the 8 kilobytes of DRAM as shared memory, and we set up the clock to 100 megahertz. So this is the design, the hardware design view from Vivaldi of the TOD with only one enclave. That enclave has the ward light connected to it. It's dedicated. So in the TE it's represented that two IPs. That is the enclave, and the rest basically is only the sync. It's the Peter Linux. So taking a look of the synthesis results, we have here the footprint of the different power cases. In green we have the TOD agents, on blue the enclaves, and on the yellow the ETCMs. So taking a closer look of the resource utilization, we can see that we have a very resource use on DRAMs. This could become a bottleneck in terms of scalability of our design, but since it's able to run up to 4 enclaves, it complies with the global platform specification, which is 2 enclaves at the same time. So taking now a look of the performance analysis, we execute a round-trip execution performance. What we mean by that is the time that took from the client application to commence an execution of a toy operation in the TA side. So we call, for example, the open session 1, then goes inside of the TA to run the open session entry point that is empty, and then come back. So we have executed these five operations. But we repeat one of them, that is the open session, to compare it with a TA already loaded and a TA that was not already loaded. We will see more detail. And then we will compare it with TopTE, that is an open source TrustZone based TE that is also compliant with the global platform specification. So I want also to take a look of the workflow and how the things are executing. So in the open session operation, we started from the client application that issues to the TOD driver through the TE client API, the open session operation. Then it communicates to the TE communication agent that there is a new operation to that specific TA. And so he asks to the TE manager agent, okay, so where is the enclave that is hosting that TA? And since we never run this command before, he then returns to asking to the TE supplicant for the location of the TA binary, so he can demand the TOD loader to load that TA to an available enclave. Once it's done, you can reset that software, and then the TE communication agent can send it to the mailbox. Then we'll issue the TI to execute that command. So this whole process has took approximately 50 milliseconds, 20 milliseconds quicker than in comparison with the OPTE. So then we repeat the same command, but since the TI was already loaded, we could skip the part of the TI manager need to load it, so it runs a lot faster, and also the OPTE is run. So then we run the evoke command, but for the sense of the TOD, it's the same behavior, so it's expected that the performance results will be approximately the same. Then we run the close session. What you need to do is kind of the same of the evoke command. It needs to call the TI to execute the final operations to close it, but then we need to erase the memory. But since we are in the FPGA, we can take advantage of the parallelism, and so we can give back to the rich execution environment that the operation has done, while we are still erasing the memory and cleaning the macro-architectural artifacts. So that's why in our TOD it's running a lot faster. So summing up all these results, I didn't take a look of the init context and the finalized context because it's only to initialize the TOD driver, and it doesn't have, it's not so interesting to show, and the performance is relatively the same, but as we can see, it's here in this graph, it's a relative performance. The OPTE is represented by one performance unit, and the TOD is blue, the two relative performance. So we can see that has performed much better because we are running on the PGA. So now this was only running toy operations. Let's now take a look of a real world application. We choose to show it the Bitcoin wallet application that was originally developed for the OPTE, and we just needed to port it for our own. So this application consists of two, the client application and the trusted application. We have 6 functionalities available. We can check if a master key was already generated. We can generate a new master key, or we can generate a new master key from a given mnemonic, or we can delete the master key. Also, we can sign a block transaction, that's what we want, and also get a Bitcoin wallet address. To perform any of these functionalities, we run this command, and we insert a 4-digit PIN, and whenever the command we are issuing, the operation has the same behavior. It opens a session, invokes the command, and then closes the session. So the setup was the same as we have evaluated, but with a little difference that we have increased the memory so we can load that TA, and we put a dedicated peripheral so we can now see what is executing on the trusted application. So on the left side we have the output from the Xilinx PT Linux, and from the right side we have the TOD. So before starting the demo, we have already run it, the check if there is a master key. There is none, so we run it, the command to generate a new master key. Now we will now we are running the wallet tree, the command tree that is generate a new master key from our mnemonic. Just wait a second, sorry. So, maybe we can do that. So, as I said, we are running to generate a new master key. Now we are asking to sign a transaction. This will take a little while. Okay, the transaction was successfully signed, as we see here from the TA side. And now we are asking for the Bitcoin address and erasing the master key. Okay, now I will pass the word to Sandro for the final thoughts. Thank you.
Okay, just to wrap up and share some final thoughts. With this work, we basically demonstrate that Reconfigurable computing, a new element in those modern SoCs, can be leveraged to provide a new and a refined key approach as an enabler to provide additional security guarantees for TEs. And as a side note, with this work, we won the Xilinx Open Hardware Contest as the PhD category, and we had the chance to basically present this innovative idea to the CTO of Xilinx. Just final takeaways. Current TEs, in particular, we focus more on TrustZone because we have this expertise. Implementations have numerous of flows, in particular the architectural ones. With that, we propose Trust Execution Environment on Demand as a novel TE design that leverages these FPGA technologies or the programmable logic available in these modern SoCs to provide TEs on a per application and per need basis. And quite important, we have demonstrated that goal that we proposed, which was compliance and compatibility with existing trusted applications. And with the Bitcoin wallet, we actually didn't change any line of code of the trusted application, and we were able to run on our model, which basically demonstrates that it's practical and is compliant. And with that Bitcoin wallet at the end of the presentation, you can also share your Bitcoins with us if you want. Okay, thank you for your time. I hope you have enjoyed the presentation, and we will gladly address some of your questions.
Thank you, guys. Big round of applause to Sérgio and Sandro. And we have a couple minutes to ask questions if you have some.
Please ask, because I will forward to Sérgio. He's a student.
Yeah, maybe I missed something, but I'm trying to understand your Bitcoin private key. Okay, do you need some kind of secret key that's in the FPGA or in the SoC in order to have your secure storage? And if so, you need some kind of key management to give it to the trusted application, to each secure enclave as you boot it up. I guess what I'm asking is, what kind of identity do you attach to the secure enclave into each TA?
Okay, that's an interesting question because so I didn't develop this Bitcoin wallet. It was originally already done, so I didn't get so much deeper. But the private key was already embedded on the application. So in my perspective was not so much on the developed on how the Bitcoin was working. It was more, okay, how can I provide the execution trust to it? Yeah, sorry.
The question is quite interesting, but the whole idea was just to demonstrate the portability. We abstract from the details in the sense that, okay, a private key is needed, a private key needs to be pegged to some sort of secure storage, but we do assume that that key is already embedded, for example, in the FPGA. Long story short, we abstracted a bit on those details, but we are fully aware of the need for this. Thank you very much.
Thank you. Any other questions? Okay. One moment. Running.
Thank you. What would be the next steps now for this project? Maybe with a vendor hat on, I'm thinking now, how many logical elements, power consumption, what happens when we have the mitigations against side channel attacks and EMC attacks, things like this? Thank you.
That's as Sandro has stated. We need an infrastructure to now see the next to the next step, which is right on track, as you said. To now we can evaluate, because we are now having a new variable in mind. We have the FPGA that we are trusting, and we can then see a lot of how well this will perform on the real use scenario, and what are the surface attack that we are creating on this type of approach. Is our next goal will be around that. We now have the infrastructure, but we now want to know how difficult it is to tear it apart.
Yeah. Here we present the resource estimation consumption for different instantiations of the number of enclaves. This gives you already an idea. The point is that this FPGA is quite small among the Xilinx UltraScale line, which means that some of the resource was already almost full with 4 enclaves, but this is a very teeny tiny FPGA in that sense. We are, as next steps, we are already planning about how we address the scalability in terms of the VRAM's resource. That is the one that is putting the bottleneck. And we have already some ideas how we can basically, while we are not using the enclaves, basically put in DRAM, but completely encrypted, because we have the FPGA, we can instantiate some crypto accelerators to basically alleviate the complexity on that. Power consumption is another very interesting metric that we didn't take into account. I mean, we have a POC. It took a significant amount of time to reach here, but still there are some open points that we will gladly address depending on the perspectives that we have in terms of funding, in terms of interest. Yeah, it's more or less like that. Okay.
Thank you, guys. Another round of applause to Sérgio and to Sandro.